Swayam Prabha. Digital India. Educated India.
So, last class I have discussed about the large scale field test. Now, this lecture I will discuss about the different types of laboratory test, okay, to measure the dynamic properties of the soil. Now, first again we have different types of low strain test and high strain test. So, these are the major low strain test apparatus, that is the resonant column test, Bender element test and ultrasonic pulse test. And high strain tests are cyclic triaxial test, cyclic simple shear test and cyclic torsional shear test. In addition to that, we can do the model test also. What is model test? Model test means in the other laboratory test we are getting basically the properties of the soil. In the model test we will get the real behavior or response of a structure itself in the lab. Okay, so I will discuss about this model test, about the seck table test and centrifuge test. So, first is what is the resonant column test. Here, this is the most commonly used laboratory test to determine the low strain cyclic properties of the soil. Fine. So, it has a solid or hollow cylinder, you can see hollow cylinder specimen. Those are subjected to harmonic torsional or axial loading. So, either it is subjected to axial loading or subjected to torsional loading. The cyclic load is applied after preparing and consolidating the specimen. The frequency and amplitude can be controlled for harmonic loads. The loading frequency can gradually change starting from low to high. That means first we give a low loading frequency, then we increase it and go to high loading frequency. The fundamental frequency of the soil is determined, which can be defined as the lowest frequency at which the response is locally maximized. So, first we will get the fundamental frequency. What is the fundamental frequency? We will see that which is the lowest frequency at which there will be the response is locally maximized. We will get the maximized locally response at the lowest frequency at which we will get the maximized locally response, that is called the fundamental frequency, that we identify. And then we will determine basically the shear modulus if the torsional harmonic load is applied, and or we will get the elastic modulus if the longitudinal loading is applied. Now, how we will get that? So, we will get by using this expression G is equal to root over V square. So, that means we should know the density of the soil, rho is the density of the soil, and Vs, velocity of the shear wave of the soil. How we will get the velocity of the shear wave? By using this expression. So, here you can see what is I. I is the, or first we will say the Fn, which is the fundamental frequency that I have already discussed. So, fundamental frequency we will identify, which is omega n divided by 2 pi. So, this what is omega? So, that also I have discussed in my previous lectures. So, how we will correlate the omega with F, that also been discussed. So, same expression I am using here. So, or it is been used here. So, that if you see my module 2 lectures, you will get all this information. So, this is the fundamental frequency in Hertz, Vs is the shear wave velocity, H is the height of the specimen, rho is the density of the soil specimen, I is the mass polar moment of inertia of the specimen, that we can measure, and I0 is the mass polar moment of inertia of the torsional loading or driving system. That should also be known. So that means here I is known, I0 is known, rho is known, Vs we have to calculate, and fundamental frequency will identify. So based on by using this expression you will get the Vs. From Vs, if we use this expression we will get the shear modulus. Similarly, for longitudinal loading, in place of I and I0 we should know the W and W0. What is W and W0? They are the weight of the specimen and loading system respectively. The I0 is the mass polar moment of inertia of the loading system. Here W0 is the weight of the loading system, and I was the mass polar moment of inertia of the specimen. Here W is the weight of the specimen. The same expression if you know, if I use here, I will get the VL. What is VL? VL is the longitudinal wave propagation velocity, and Es is the elastic modulus. Once I will get the VL by using this expression, I will get the elastic modulus. So that means here I will get the shear modulus as well as the elastic modulus depending upon which type of loading I am using or applying. Now generally when the strain level is lowest in the center of the specimen and highest at the edge of the specimen if I use the solid specimen. So just to avoid that or minimize this variation of the shear strain along the specimen, the hollow specimens are used, okay, to minimize the variation of the shear strain amplitude across the specimen. So if I use the solid specimen, there may be a variation of the shear strain across the specimen. To avoid that, to minimize that, we can use the hollow specimen also. The measurement of poured water, though the measurement of poured water pressure is difficult in this test. Okay. The next test, that is the Bender element test. So what is Bender element test? So in Bender element test, the shear wave velocity of the soil is measured. Okay. So for shear wave velocity of the soil is measured. The two piezoelectric material are bonded together. Now if I draw this Bender element setup, suppose this is the two piezoelectric material, they are bonded together. Two material, they are bonded together, and suppose this is the base. Now voltage is applied to bend the entire element. So when this is a different voltage is applied, so this material will bend because these are two piezoelectric material. If there is a voltage change, then they will bend. So they will bend like this. Suppose if there is a negative voltage, so they will bend like this. Okay, in this direction. If there is a say positive voltage, then they will bend in this direction. So they will bend like this. Okay, so that means you can say these are this direction, the soil particle will move. This is the soil particle. Okay, so now when this entire element will bend, now the lateral displacement of the bender element produce the voltage. Okay, now if the voltage is applied, they will bend. Because of this bending, they will also create or produce voltage. Okay. So that means that Bender element can be used as wave transmitter as well as receiver, because when you apply the voltage they will bend, and because of this bending the voltage will create. So that means it can be used as both wave transmitter and receiver placed to opposite end of the soil sample. So these elements are placed to opposite end of the soil sample. So that means then what will happen? A voltage pulse is applied in one end, this bender element, one is applied to transmitter element which is produce shear wave. So that means one end we apply the voltage pulse, so that will produce the shear wave. Okay, so that is called the transmitter element. Where we apply the voltage pulse, it will produce the shear wave. Now, shear wave will travel through the soil sample and reach to the other end of the sample, where also we have placed another element. Okay. Now, now when it reach to the other side, there also a pulse will create. Okay. Now, the soil sample is not disturbed during the test, thus can be used for other soil characterization. Okay. So that means one side the pulse is applied, so shear wave, that is the transmitter element, and the shear wave will generate. That shear wave will travel to the soil sample and it will reach to the other side of the soil sample. There also another element is placed which is called receiver. So there will be another pulse will generate. So that means we will note down the travel time of the shear wave velocity of shear wave. Now, if I know the height of the soil sample, and if I note down this travel time of generation and of the shear wave and receive of the shear wave to other ends, then you will get the velocity of the shear wave. We know the height or travel distance, and if we note down the travel time, okay, by generating and the receiving the shear wave, then we will get the velocity of the shear wave. And once we get the velocity of the shear wave, then we will, by using the G equal to rho Vs square, you will get the shear modulus of the soil. Clear? So, next one is the ultrasonic pulse test. So, in this test, wave propagation velocity, either P wave or S wave on the soil sample are measured. Okay. Ultrasonic transmitters and receivers are attached at two ends of the soil sample. Similar like the Bender element, we attach transmitter and the receiver two ends of the soil sample. It is very useful for soft material as test can be done keeping the soil sample in the sampling tube. So, it is very soft material, we can keep it in the sampling tube and we can conduct the test. Now, if we generate the P wave, so then we will get the constant modulus, that is M. What is M? M is the constant modulus and Vp is the velocity of the P wave. Once you get the constant modulus, then by using this expression, I will get the elastic modulus also, if I know the Poisson ratio mu. And if I generate the shear wave, then I will get the shear modulus. Okay. So, the advantage is that this test can be done keeping soil sample in the sampling tube. And another advantage of the Bender element test is the soil sample is not disturbed during the test, thus can be used for other soil for determination for other soil characteristics. Okay. So, now next, these are the low strain test, laboratory test. Next was the high strain laboratory test, that is the cyclic triaxial test. So, this is the most commonly used laboratory test to determine the high strain dynamic properties of the soil. So, for most commonly used determination of low strain dynamic property of the soil in lab is resonant column, and for triaxial it is the most commonly used laboratory test to determine the high strain dynamic properties of the soil. In this test, deviatoric stress, difference between your axial stress and the radial stress, is applied cyclically. Okay? The test is conducted either under stress control condition or under strain control condition. Generally, tests are performed keeping radial stress constant. Radial means your all-round stress. And axial stress is applied cyclically at a frequency of around 1 Hz. The measured stress and strain can be used to compute the shear modulus, basically, or elastic modulus. Actually, in a triaxial cell, we are basically calculating the elastic modulus. Then we are converting it to shear modulus and the damping ratio. Damping ratio also you can use. We can calculate. Okay. Next one is the cyclic simple shear test. This earthquake stress condition are produced much more accurately in cyclic simple shear test than the cyclic triaxial test. That is the advantage of this test. That means here earthquake stress condition are produced much more accurately as compared to cyclic triaxial test. It is most commonly tested for related to liquefaction. The cylindrical short soil specimen is restrained against the lateral deformation. The cyclic horizontal stress is applied to the top and bottom of the soil specimen. Basically, it is shearing, and shearing is applied. The soil test specimen is deformed in similar way like an element of soil subjected to vertically propagating S wave. The diameter and height ratio should be taken as greater than around 8:1. Okay. So, third one is the cyclic torsional shear test. So, this test is used to determine the stiffness and damping characteristics over a wide range of strain level. It is used for a wide range of strain level, and same as cylinder, cyclic torsional shear testing apparatus is used to minimize the variation of the shear strain across the soil sample. Now, if I summarize all these tests, the cyclic triaxial test, here we will get the shear modulus? No. Direct, I am talking about the direct measurement. Shear modulus? No. We will get the elastic modulus. From there, by using the correlation, you will get the shear modulus. So, these are what are the things directly I will measure from this test. Cyclic triaxial test, I will measure elastic modulus directly and the damping ratio or the material damping. Cyclic simple shear, here I will get the shear modulus because here shearing is applied, but elastic modulus directly I cannot measure, but the damping of the material can be measured. Cyclic torsional shear, here shear modulus can be measured directly, not the elastic modulus, but damping of the material can be measured. Resonant column, here both, that means the elastic modulus and shear modulus both can be measured. Damping ratio or the damping, material damping, yes, this can also be measured. But ultrasonic pulse test, here also shear modulus and elastic modulus both can be measured, but not the damping. Okay. So, these are the summary of different tests. Now, I will talk about the model test. The two types of model test I am talking about, that is the shake table test and the centrifuge test. So, in the shake table test is what? Where in the shake table and the centrifuge, here I will get the actual or the response of the structure, actual response of the structure. In the other laboratory test, you will get the soil properties. Here I will get the actual behavior of the structure under earthquake loading or dynamic loading. So, here you can see that this is a shake table facility of IIT Kharagpur. So, here we have the one dimensional table, another this is the 6-dimensional table. 6-dimensional means I have already discussed that there are 3 translation movement 2 horizontal, 1 vertical, and 3 rotational movement. That means 6 types, 6 movements. 3 rotational, 3 translation. But this 1D table, it is only 1 horizontal translational movement is possible. This testing facility. That means it move only in 1 horizontal direction. 1 translational movement is possible, that is horizontal movement. That is the 1D SEC table. Here it is 3 translational movement and 3 rotation. All 6 types of movement at the same time is possible in this facility. Okay. So, this is, you can see, this is this movement is applied to a dynamic actuator. This is the table and this is the model tank, inside which we will place our structure and then we will shake it and we will get the response. Then we have to use different instrumentation. You can measure the displacement, stresses, acceleration with time, so, or pore pressure. So, all these things you can measure if you use the different instrumentation. Clear? And in the centrifuge test, in case of centrifuge test, a rotation is applied with a rotational speed of root over n by r to produce an acceleration at the model location, which is n times the acceleration of gravity, where n is the scale factor and r is the distance of model from the axis to centrifuge. Clear? What does it mean? That you can see, this is the model tank. This is the your centrifuge tank, inside which we will place that our structure, geotechnical structure, or the structure that we will want to test. Now you have to rotate it with a rotational speed of root over n by r. What is n? N is the scale factor, that I will discuss, because that is the advantage of centrifuge test over the SEC table test. That is your n, so that we can produce an acceleration which is n times more than the acceleration of gravity. That means in this test, in the model tank, the acceleration is ng, if g is the acceleration due to gravity. So, and here the acceleration is n times of g. Clear? And r is the distance between model and axis of centrifuge. This is the axis of centrifuge and this is the model. This is the centrifuge facility of University of California, Davis, which this photograph is taken from this source. So, here you can see, now what is the advantage of this centrifuge over the SEC table? So, now when talking about this laboratory scale test, scaling is a very important issue, because actually the real structure we are scaling down and we are doing the test. That means we have to take care about the scale effect. So, let me discuss about the scale factors or scale effect of different quantities for SEC table and the centrifuge. So, if you see that, or before that, I want to mention that if you want to get the more information about the scaling of SEC tables, you can read this paper. Okay, I am giving the reference. So, every time I am saying that I will give the reference and I will give some reading assignment, so that you will read these papers and get more information. So, here I will give you the some information. So, and I am giving the scaling of few quantities. So, you will get the other quantities, how to scale under different condition, you will get from this source. If you read this paper, you will get more information about the scaling under SEC table. Okay, so now if I concentrate now these quantities only. So, as I mentioned, the acceleration, if this is your model dimension divided by the prototype dimension. So, and this is SEC table, this is centrifuge. So, model length wise, obviously model length will be n times lower than the prototype length. So, that is why the model dimension by prototype dimension will be 1 by n, and that is true for both SEC table and the centrifuge, because we will scale down the dimension. So, that means my prototype dimension is n times more than the model dimension, or the real dimension is n times more than the real dimension. What is n? N is the scale factor. Now, if I consider my density and the strain are same for prototype and the model, so now your density and strain level can be different also. So those things you will get in this paper. You just read it. But here I am considering that the density, the same density in the soil and the same density in the soil in the prototype and the model is considered, and the strain level is also same. If this is the condition, if these two conditions are satisfied, then you can see the stress in the shake table is n times less than the stress of the model. That is the problem, because here we cannot generate the real stress condition in the lab in case of shake table. But if we want to generate that, what is the option? Then your n value should be 1. That means the model dimension and your prototype dimension should be same. That means the same size of model or the same size of prototype model you have to consider or you have to build inside the lab, which is difficult. So that means here the stress is always less than the actual stress. Model stress is less than the actual stress. But that means if you make a model as big as possible or close to your prototype, then these limitation will be reduced. That means now you can produce the stress which is close to the actual stress condition or the prototype stress condition. But most of the cases it is not possible inside the lab. So that's why that is the problem in shake table test, where we cannot generate or produce the same stress level inside the lab. But if you see that the centrifuge, this value is 1. So that is the advantage in the centrifuge, that here we can generate the same stress level within the lab. Same means the same as the prototype. Clear? So let me just, I will give you one or two things that how this stress level is coming for first shake table and the centrifuge. Okay. So that is a simple way I will discuss that for this stress. Okay. Stress we know that is your force by area. Okay. Now force will be mass into acceleration, mg divided by area. What is mass? Mass is velocity, volume into density, that is mass, into g divided by area. Now what is your volume? Volume, if it is L cube, length cube, this is the rho is the density, this is g, area it is L square. So now if I get, then this will be L rho g, that is the stress. Clear? Now for the stress for model divided the stress for prototype, okay, that will be equal to L rho g model divided by L rho g prototype. Okay. So now you know that we have considered density is same for prototype and the model. So this rho will cancel. Now for shake table, g acceleration is same as the model acceleration, prototype acceleration. Model acceleration and the prototype acceleration, that is same. Okay, because the same. But in case of centrifuge, the model acceleration is n times more than the g. But in the shake table it is 1. So that means the rho g will cancel. So it will be only L model by L prototype. Now what is L model by L prototype? You can see that we know that prototype length is n times more than the model length. So, it will be basically 1 by n. That is basically stress is 1 by n. So, that is for shake table. Okay. That is for shake table. Now, for centrifuge, the same thing we are doing, but the problem is in case of centrifuge, this is L rho G, this is L rho G for model, this is for prototype. But for centrifuge, rho will cancel. This is also again 1, this density, but not the G, or I should say it is acceleration, not the gravity. I should say it is acceleration. So, in the model, the acceleration is n times of the G. In case of centrifuge, n times of G, but in the prototype, it is G only. So, again this G will cancel, it will be L model divided by L prototype into N. So, but again L model and L prototype, this is be N L into N. So, it will be 1. Clear? That is for centrifuge. So, this way you can get the what is the would be the force, then in the time also you can get, that is also interesting thing. So, I will do few more cases. So, that means you can see gravity is 1, this is 1, this is n, and similarly force also you can get. What is force? Force is V rho G. Okay, rho G will cancel. In V it will be force for centrifuge, it will be n 1 by n cube, but for the centrifuge it will be 1 by n square. But the stress level is same in case of centrifuge, prototype and the model. But now the time, if you look at the time, that is very important. So, let me discuss the time. So, I will discuss the few cases, that suppose how we will do the EI value. EI value check also you can do, that for EI, if I do the EI. So, EI is again E is your force by area and I is L to the power 4 by 12 moment of inertia. So, it will be in force, it will be L cube rho G by L square into L to the power 4 by 12. So, it will be rho G L to the power 5 divided by 12. So, for shake table, your rho G L 5, 12 I am cancelling, rho G L 5 for model, for prototype, that will be equal to this rho G cancel, it will be 1 by n to the power 5. Okay. So, for centrifuge, this will be how much? Rho Ng L to the power 5 divided by rho G L to the power 5. This is model, this is prototype. So, this will be 1 by n to the power 4. Similar way you can get the EA value also, for you scale down that. Okay. So, next I am doing for the time, the last one, the time, that we know G is equal to L by T square. T is the time. So, that means your time is equal to L by G to the power half. So, for shake table, that your L by G to the power half model by L by G to the power half prototype. So, this will be G will cancel. So, this will be L M by L P to the power half. So, this will be 1 by N within root. That is for shake table. Now, for centrifuge, it will be your again L by Ng divided by L by G. This is prototype, this is model. So, your G will cancel. So, it will be L model by L prototype divided by N, 1 by N to the power half. So, this will be 1 by N into N to the power half. So, this will be 1 by N. You can see this is 1 by root n, it is by n. So, that means you can see here, suppose if your duration of earthquake is 50 seconds and your scale factor is say 49, or your duration of earthquake is 49 seconds and the scale factor is 49. N value is 49 and duration of earthquake is also 49. Then what would be the duration of the shake table test as per these scaling laws? So, it will be 49 divided by root over 49. So, it will be 49 by 7. So, it will be 7 seconds. So, if your duration of earthquake is, or the loading is say 49 seconds and scale factor is 49, then duration of the shake table test should be 7 seconds. But in case of centrifuge, it is just 49 divided by 49, just 1 second. Okay. So, you can see, so that is why these in a centrifuge, it is very for doing dynamic test or the seismic test, you have to use very sophisticated instrument. The instrumentation should be very sophisticated, so that you can measure all these your quantities within very short duration of the time. Okay, so this is your I have discussed, but again I am telling that these are the simple way I have discussed about these scaling things, but there are other quantities also, that also you can scale down, but here it is assumed the density and strain are same as the prototype. In the model, density and strain are same as the prototype, but that can be different. If that is different, then what would be the case? So, and this all in the detailed thing you will get in this paper, you can read it. Okay. So, thank you. So, this is the end of this lecture. So, in the next lecture, I will discuss that how I will use these properties. Okay. So, that we will get from these tests. Okay. Thank you.